Hi students, this is a video on derivatives involving hyperbolic functions. Make sure you've already watched my introduction to hyperbolic functions video before you watch this one. Now hyperbolic functions are sometimes called hyperbolic trigonometric functions because they are a lot like trig functions. But I go over that in detail in the previous video. Okay, so here we're going to be focusing on derivatives. Now, if you look at a formula sheet, the one that I post on Canvas, the formula sheet, formulas from Calculus 1 and Calculus 2, on the very first page, past the derivatives and antiderivatives, you're going to see hyperbolic functions. And of course, you got the classic ones here, Cinch of x equals e to the x minus e to the negative x over 2, cosh of x equals e to the x plus e to the negative x all over 2. Now these right here are not actually derivatives. These are just the definitions of the two functions. But then here you have a bunch of derivatives. And a lot of these work just like the regular trig functions. So just like you would think, the derivative of Sinch of u is equal to cosh of u times du dx because of the chain rule. But the one that's different is the derivative of cosh of u. Instead of being negative Sinch of u, it's actually positive Sinch of u times du dx. So this one is a little bit different. So we're just going to be focusing on these first two for our first example. So the derivative of Sinch is cosh, and the derivative of cosh is Sinch. Now remember, with regular trig functions, the derivative of sine is cosine, but the derivative of cosine is negative sine. So the difference is right here in this formula for the hyperbolic functions. Okay, so we're going to see an example, a relatively easy example to start off with. Okay, so example, find each derivative. Find each derivative. Okay, and for problem number 1, we want to find the derivative of y equals 9 times Sinch of x over 3. Y equals 9 times Sinch of x over 3. All right, so all we really have here is a constant times Sinch of x over 3. And so we can just call this x over 3 u. Okay, so we're going to call the x over 3 u. So for our derivative here, we're really taking the derivative of 9 Sinch of u. Okay, and like I just said, from your formula sheet, the derivative of Sinch of u is the same as cosh of u times du dx. Okay, but we also have a 9 here, so it's going to be 9 times cosh of u times du dx. Okay, and that's going to be our derivative, so that's going to be our dy dx. Okay, but now we can go ahead and plug back in the original expression in terms of x. So we said that u was x over 3. Okay, so what we're going to have here is 9 times cosh of x over 3. Okay, 9 times cosh of x over 3. And then we have times du dx. So what is the derivative of x over 3? Well, that's just going to be 1/3 because the derivative of x is 1, but then 1/3 is a constant and the constant stays there. So it's going to be times 1/3. Okay, so you should have 9 cosh of x over 3 times 1/3. Okay, 9 cosh of x over 3 times 1/3. And then, of course, 9 divided by 3 is 3. So we can cancel those out. Okay, so our answer is going to be dy dx equals 3 times cosh of x over 3. And that's actually the whole problem. And if you feel comfortable with it, you can even skip writing it as u, because you're really just doing the chain rule here. You're just taking the derivative of the outer function, Sinch, which ends up being cosh, inner left alone, and then you multiply that times the derivative of the inner function. So the derivative of x over 3 is 1/3. So if you don't want to go with this business of writing u, you can actually just do the outer inner rule. Derivative of the outer function, inner left alone, times the derivative of the inner function. And then boom, you're done. And then you don't even have to use u. Okay? But that's the whole problem. So that first one should be relatively easy. Okay, if only they could all be that easy. So, for problem number 2, the difficulty is going to go up quite a bit. So for problem number 2, we want to find the derivative of y equals 6 root t, y equals 6 root t. I've been told that my 6's look like b's, so I'm trying to work on that. 6 root t times tanch of root t. 6 root t times tanch of root t. So now this one is going to be some more work to take the derivative of. But notice we have something multiplied times something else. So remember, if you're taking the derivative of something multiplied times something else, you want to label the two things and then use the product rule. Okay, so we're going to call the 6 root t, that's going to be our u. And then the tanch of root t, that's going to be our v. And then we use the product rule. Okay, so how does the product rule go? Well, the product rule we've seen many times in this class already, so hopefully you remember it. It just says that your derivative, y prime, is going to be uv prime plus u prime v. Okay, so here it's going to be dy dt equals uv prime plus u prime v. And here our u is 6 root t, and our v is tanch of root t. Okay, so obviously we're going to need to calculate our u prime and our v prime in order to be able to plug them into the formula. So let's do that over here. Okay, so since u is 6 root t, what is u prime going to be? Well, for u prime, the 6 is a constant, so it stays out front. And then what is the derivative of the square root of t? Well, remember, the square root of t is the same as t to the 1/2 power. So actually, I can write that here. So u is going to equal 6 times t to the 1/2 power. And then u prime is going to be the derivative of that. So we're going to go ahead and use the power rule. So we go ahead and bring the 1/2 out front, and we decrease the exponent by 1. So we're going to have 6 times 1/2 t to the negative 1/2. Okay, so all I did there was I did the power rule, so I brought the 1/2 power out front. And then I decreased the exponent by 1. So I did 1/2 minus 1 is negative 1/2. Okay, and then the 6 and the 2 cancel out. And we get 3 on the top. Okay, so we're going to get u prime equals 3 over t to the positive 1/2. So what I did there is 6 divided by 2 is 3 on the top, and then on the bottom, I went ahead and I moved this t to the negative 1/2 down to the denominator, like we always do. and then that became t to the positive 1/2. But then what we can do here is, now that it's t to the positive 1/2 again, we can rewrite that as the square root of t in the denominator. Okay? So in our denominator here, we're going to have the square root of t. So we have u prime equals 3 over root t. All right. And then we still need to calculate our v prime. So our v prime is going to be the derivative of tanh of root t. So that's going to be quite a bit of work. So first of all, let me just write down v. So here v was equal to tanh of root t. Tanh of root t. Okay, so v prime is going to be the derivative of that. But this is actually a composite function. So it's got an inner function and an outer function. So our v prime is going to be the derivative of the outer function, which is tanh. Inner left alone. So for that, what is the derivative of tanh? Well, we go back to our formula sheet, the formulas from Calculus 1 and Calculus 2. We see the derivative of tanh of u is sech squared of u times du dx. So notice this one's actually the same as the standard trig functions, because remember the derivative of tangent is secant squared. So it should make sense that the derivative of tanh is sech squared. Okay? So hopefully there's no surprises with that one. Okay, so taking the derivative of the outer function, inner left alone, we're going to have sech squared of the square root of t. So notice I just left the root t alone. But now we have to multiply this times the derivative of the inner function. So we're going to have to multiply this times the derivative of the square root of t. So I'll write square root of t prime. Okay, so I took the derivative of the outer function, tanh, inner left alone. So that gave me sech squared of root t. And now I'm multiplying this times the derivative of the inner function. And you could also have called it tanh of u if you wanted to do it that way, just like we did on the earlier problems. But I like to mix it up a little bit because different people like to do these different ways. So I wanted to show you all the different ways. Okay, so what is the derivative of root t? Well, once again, instead of writing it as root t, let's write it as t to the 1/2. So we're taking the derivative of t to the 1/2 using the power rule. So we go ahead and bring the 1/2 out front, and we decrease the exponent by 1. Okay, so that's going to be 1/2 t to the negative 1/2. Okay, 1/2 t to the negative 1/2. And then if we move the t to the negative 1/2 to the denominator, it becomes t to the positive 1/2, which becomes square root of t. Okay, so what we're going to end up here with is we're going to have v prime equals sech squared of root t times 1 over 2 root t. Because we have 1/2 t to the negative 1/2, move that down to the denominator, it becomes 1 over 2 root t. Okay, so there's our v prime. So this is a long problem. We just calculated u prime, which was 3 over root t, and v prime, which is sech squared of root t times 1 over 2 root t. Now, we still have to plug all this into the product rule. Okay, so in the product rule, we have y prime equals uv prime plus u prime v. Okay, so y prime here is going to be dy dt, because remember in this problem, our original variable was t. That's our independent variable. So y prime is going to be the same as dy dt. Okay, so we have dy dt equals uv prime. So let's see, u was 6 root t. Okay, so we have 6 root t for u. And then we have v prime, which we just calculated, was sec squared of root t times 1 over 2 root t. Okay, so sec squared of root t times 1 over 2 root t. Okay, so there's our v prime. So we got here, what we have here is u times v prime. That one right there is v prime. And then we have plus u prime v. Okay, so what was our u prime? In this problem we said u prime was just 3 over root t. Okay, so we have plus 3 over root t times v. And v, we said at the beginning of the problem, is tanh of root t. So we're going to have 3 over root t times tanh of root t. I'm going to have to erase this over here so I have room. Okay, so 3 over root t times tanh of root t. And that right there was our u prime, which we said was 3 over root t times our v, which at the beginning of the problem was tanh of root t. Okay, so hopefully that makes sense. That is the product rule all written out. Now we can simplify this a little bit, but we don't have to go very far with the simplifying. Fortunately, we're not going to end up having to do any crazy identities or anything to simplify this. The only thing we need to do is cancel out this 6 root t and the 2 root t for this first term. Okay, so for the first term, we know that 6 divided by 2 is 3, so we're going to have a 3 on the top. And then we also know that the root t's here are going to cancel. We have a root t on the top and a root t on the bottom, so those cross out. Okay, so that's actually going to bring us to our final answer. So we're going to get dy dt equals, we're just left with 3 times sec squared of root t, 3 times sec squared of root t, plus, well, the way they wrote it on my math lab is they went ahead and multiplied the 3 times the tanh root of t on the top for our numerator, so they have 3 times tanh of root t on the top, and then on the bottom we have a root t. Okay, so the only thing they really changed in their answer was they went ahead and multiplied the 3 times the tanh root t on the top, and then they wrote that all over root t on the bottom. Okay, and that brings us to our final answer. So I know that one was a lot harder than the first one. But it's good that I show you an example of each type of problem so that you don't hopefully have too many surprises when you're doing your homework. Or the quiz for that matter. Okay, so that was our second example. That was problem number 2. So let's go on to our third example. Now if you're already brushed up on your Calculus 1 stuff, most of this should be pretty straightforward, because you're just using these new formulas, but you're still using all the stuff from Calculus 1, which is the chain rule, the product rule, the quotient rule, any of those things. They're all topics from Calculus 1 that hopefully you are familiar with by now. Okay? So for problem number 3, we want to find the derivative of y equals natural log of parentheses cosh of 3z. Okay? Y equals natural log of parentheses cosh of 3z. So here our independent variable is z, just like t was our independent variable in the last problem. So taking the derivative here, you need to be familiar with the chain rule. And remember, with the chain rule, that's when you have a composite function. Okay? So with a composite function, you have an outer function and an inner function. Sorry, I was just having a little trouble with my recorder. That's what you saw there on the screen there. I think it's working again now. Okay, so anyway, like I was saying, you have a composite function, you have an outer function and an inner function. And it's called the outer inner rule because you take the derivative of the outer function, inner left alone, times the derivative of the inner function. But on this one, we actually have three functions in one. So we've got our outer function is ln, and then our middle function is actually going to be cosh, and then our innermost function is 3z. Okay, and the way you do the chain rule is you work from the outside inward, just like the similar problems I did with other functions in previous lectures. Okay, just now we're doing a hyperbolic function. Okay, but what we're going to have here is we're going to have our y prime, or dy dz, equals the derivative of the outer function, middle and inner left alone. Okay, so the derivative of outer function ln is 1 over the middle and inner function, so that's going to be 1 over cosh of 3z. Okay, so right there, I just did the derivative of the outer function, middle and inner left alone. Now we do this times the derivative of the middle function, inner left alone. Okay, so the derivative of cosh, we said, was just Sinch. So that's going to give us Sinch of 3z. But notice I left the inner function alone. So right there, I took the derivative of the middle function, inner left alone. Because remember, the derivative of Sinch is cosh, and the derivative of cosh is also Sinch. There's no negative there. Okay? And then we finally do this times the derivative of the inner function. So what is the derivative of 3z? Well, the variable goes away, so we just get 3, which is a constant. Okay, so this is going to be times 3. So there we are working from the outside inward using the chain rule. Okay, and then of course we can simplify this a bit. So this 3 we can bring out front. Okay, so now we have dy dz equals 3 times, well, in the numerator we have Sinch of 3z, and then in the denominator we have cosh of 3z. Well, let's see here. Sinch over cosh. Doesn't that sound an awful lot like sine over cosine? Well, remember, sine over cosine with regular trig functions is actually tangent. And if you watch my earlier video where I talked about an introduction to trig functions, on your formula sheet, not on the first page, but actually if you go to the 4th page of your formula sheet, we have the hyperbolic identities. And tanh of x is actually sinh of x over cosh of x. So this sinh of x over cosh of x, that simplifies to tanh of x, just the same way as sine over cosine gives you tangent. So that's actually what we're going to do to finish simplifying this here. So here, instead of x, we have 3z, but as long as it has the exact same expression, we can use the identity. Okay, so instead of writing sinh of 3z over cosh of 3z, we can write that as tanh of 3z. Okay, so we have 3 times tanh of 3z. And that's our dy dz, which is our derivative. That's our answer. Okay? Cool. So that one went a little bit faster than the second one. The second one took us a while. Okay, wanted to do a couple more. So that was problem number 3. Let's take a look at problem number 4. or example number 4. Now this one is long, but hopefully it's not too difficult if you know what you're doing. So for this one, we have y equals cosec. So that's hyperbolic cosecant, but I say cosec. So it's cosec of 2 theta times the quantity 1 minus ln of cosec of 2 theta. Let me zoom out a little bit here so I actually have room. So we have y equals cosec of 2 theta times parentheses 1 minus ln of cosec of 2 theta. Now I was just going to let you guys try this one on your own, but it is pretty long, so I think it's probably better if I just do an example of it, because I don't want anyone to get lost or confused. So it has so many parentheses that it's going to take a while to simplify it. But what I would recommend doing here is, since you have something times something else, and you're taking the derivative, you want to use the product rule. Okay, so you label the first function, which here is cosec of 2 theta. That's going to be our u. And then our second function, which is 1 minus ln of cosec of 2 theta. That's going to be our v. Okay, and then we go ahead and use the product rule. I'll just write PR for product rule. And because our independent variable here is theta, it's going to be dy d theta for the derivative. So we're going to have dy d theta equals uv prime plus u prime v. That's just the standard product rule that you always use when you have two things multiplied together. And the other thing you could have done here is you could have distributed the cosec of 2 theta at the beginning if you wanted to, but then you would end up having to take the derivative of 2 terms, so I don't know if that would really be any easier, and you'd still end up having to do the product rule. So I'm just doing it this way. Okay, so what we're going to need to calculate here is u prime and then also v prime in order to plug them into the product rule. Oops. Okay, so let's start with u prime. What is the derivative of cosec of 2 theta? Let's do that over here. Okay, so u prime is going to be the derivative of cosec of 2 theta. Now going to our formula sheet on the first page, the derivative of cosec of u is negative cosec of u times coth of u times du dx. So here we're going to have negative cosec of 2 theta times coth of 2 theta times the derivative of 2 theta. But if that's too much to see all at once, you can write down your u. So here our u was cosec of 2 theta. And then taking the derivative, we get our u prime is going to be negative cosec of 2 theta coth of 2 theta. So that was the derivative of the outer function. Here the outer function is cosec, the inner function is 2 theta. So the derivative of cosec, the outer function, is actually negative cosec times coth. And here we have 2 theta instead of u. And now we multiply this times the derivative of 2 theta. That's the inner function. So I took the derivative of the outer function, which gave us the negative cosec times coth, inner left alone, and now I'm multiplying this times the derivative of the inner function. So what is the derivative of 2 theta? Well, remember theta is just our variable, just like x. So what's the derivative of 2 theta? Well, that's just going to be 2, right? Because the variable goes away. Okay, so that means our u prime, if we bring the 2 out front, we have negative 2 cosec of 2 theta times coth of 2 theta. Okay, so there's our u prime. And then what else do we need to calculate here? Well, we also need to calculate v prime in order to use that in the product rule. So here our v was 1 minus ln of cosec of 2 theta. So that's quite a mouthful. So v equals 1 minus, we said ln of cosec of 2 theta. And this is one of those problems that's so long that you have to have a lot of patience to get through the whole thing. Okay, so anyway, our v was 1 minus ln of cosec of 2 theta. And so our v prime is going to be the derivative of this. So what's our v prime going to look like here? Well, for our v prime, the derivative of, let me actually go over here so I have room later. The derivative of 1 is 0, because the derivative of any constant is 0. So this is just going to go to 0. And then to take the derivative of negative ln of cosec of 2 theta, just like the last example that we did, we have to work our way inward. So we're going to start with the outer function, take the derivative of the outer function, middle and inner left alone, and then we're going to multiply that times the derivative of the middle function, inner left alone, and then multiply that times the derivative of the inner function. So it's a lot, I know, but once again here we've got, here our outer is negative ln, our middle is cosec, and then our inner function is 2 theta. So working from the outside inward, we're going to get v prime equals, well, the derivative of ln is 1 over. Okay, and we have a minus out front. So we have negative 1 over cosec of 2 theta. Okay, so negative 1 over cosec of 2 theta. That's the derivative of the outer function, middle and inner left alone. And then we multiply this times the derivative of the middle function. So what is the derivative of cosec? Well, it's complicated, but we just said the derivative of cosec is negative cosec times coth. Okay, so this is going to be times negative cosec of 2 theta times coth of 2 theta. So this problem is really relentless. So here we did the outer function, and then we just did the middle function. And now we have to multiply this times the derivative of the inner function. So the derivative of 2 theta is just going to be 2. So we're going to have times 2 at the end here. Okay, that's your inner function. But even though it's really complicated here, we do fortunately see some things cancel out. So we'll notice right off the bat that the cosec of 2 theta on the top and the bottom cross out. And then the minuses are also going to cross out. So all we're going to be left with is 2 coth of 2 theta. So even though it was hard to calculate, fortunately some stuff crossed out, so it's not so long to write it down. So we're just going to have 2 coth of 2 theta for v prime. 2 coth of 2 theta. And remember, once again, these are all hyperbolic functions. That's why they have h's. And I say coth of 2 theta, but what I mean is hyperbolic cotangent. It just takes a long time to say that, so people just say them the way they're written. Okay, so we've got our u prime and our v prime. So now we're ready to plug everything into the product rule. So writing out lots of room here for the product rule, we have dy d theta equals u v prime. Okay, so in this problem, u was cosec of 2 theta. So we have cosec of 2 theta for u times v prime. Well, what was v prime? Well, we just calculated it. V prime, we said, was 2 coth of 2 theta. Okay, so here, whoops, our v prime was 2 coth of 2 theta. So here we've got u, and then here we've got v prime. And then we also need to have plus u prime v for the product rule. So for our plus u prime v over here, well, our u prime, we said, was negative 2 cosec of 2 theta coth of 2 theta. Okay, so I'm going to run out of room there. So I probably should actually erase a little bit of this so I have some room. Okay, so we got our u prime, which is negative 2 cosec of 2 theta coth of 2 theta. Negative 2 cosec of 2 theta coth of 2 theta. Ooh, that's a long one. That's u prime. And then we have to multiply that times v. So here v was this whole business here. So 1 minus ln of cosec of 2 theta. So I'm going to have to erase all this so I actually have room. Okay, so we have u prime times v here, and our v was unfortunately rather long, 1 minus ln of cosec of 2 theta. 1 minus ln of cosec of 2 theta. Whew, that's a lot to write. Okay. And you would hope that you'd be done, but of course you can simplify this a bit. So what can we do to simplify all this? Well, let me zoom out so we can actually read the whole thing. So what we've got here is uv prime plus u prime v. Now some stuff is going to cancel out. First of all, for the uv prime, that's going to be 2 cosec of 2 theta coth of 2 theta. So we have 2 cosec of 2 theta coth of 2 theta. And then we have over here, if we distribute our u prime to each of those terms, I can do that. So I can actually distribute this to each of those terms, which is going to be a little bit ugly, but I don't know what else to do here. That's just how the problem is. So we're going to have, for the first term, we're going to have minus 2 cosec of 2 theta coth of 2 theta. Sorry, it's getting difficult to write this small. Maybe I should zoom in again. Okay, so for that first term, we have negative 2 cosec of 2 theta coth of 2 theta. And then distributing it to the second term, the minuses are going to cancel. So for the second term, we're going to have positive 2 cosec of 2 theta coth of 2 theta times natural log of cosec of 2 theta. Whew, that's hard. Okay. So I'm just going to write that down below here. So we're going to have plus 2 cosec of 2 theta coth of 2 theta times ln of cosec of 2 theta. Well, good thing I'm doing this one, because this is a really hard problem. Starting to regret putting it on your homework a little bit, but at least you can watch through this video. And in case it looks too tiny to read, what we did here, let me zoom in again, was here we got our first term, our uv prime, that's this right here. And then we distributed the u prime over here. So when we distributed this negative 2 cosec coth to the 1, that gave us this right here. And then when we distributed the negative 2 cosec coth to this term, the minuses canceled out, and we got 2 cosec coth times ln of cosec. So that's what gave us, zoom out a little bit again, that's what gave us right here, 2 cosec coth ln of cosec. Okay, now why did I bother to do all that? What happens now? Well, hopefully some of you have already noticed what's going to happen here. This one, 2 cosec of 2 theta coth of 2 theta, and this one, negative 2 cosec of 2 theta coth of 2 theta. Those are like terms, and they're opposites, so they just cancel out. So thankfully, after all that work, we do get to cross these out. So all we're really left with was when I distributed this negative 2 cosec of 2 theta coth of 2 theta to this term, and the minuses canceled out, this is all we're left with. So 2 cosec of 2 theta coth of 2 theta times ln of cosec of 2 theta. Okay, and that's actually going to be our final answer. Okay, so 2 cosec of 2 theta coth of 2 theta times ln of cosec of 2 theta. Right, and that's going to be our final answer. And let me just make sure that's what they got on my math lab, because that's an awfully long problem. 2 cosec of 2 theta, good. Times coth of 2 theta, good. Times ln of cosec of 2 theta, also good. Whew, that's a tough problem. Well, hopefully this video will help with that problem. It's mostly tough because there's so much going on, it's easy to forget something. Okay? Alright, so I think that was example number 4 that I just did. Yeah, that was example number 4. So let me zoom back in, back to a normal zoom, and we're going to take a look at problem number 5. Okay, so example number 5. So now this one's interesting. Here we want to find the derivative of y equals Cinch inverse. Okay, so that's Cinch to the negative 1 power, is what it looks like it says, of 5 root 5x. Now that's not actually Cinch to the negative 1 power. What that really is Cinch inverse. So that's an inverse hyperbolic sine, which I know can be kind of intimidating because you learn these new functions and they have a fancy name, and then you have the inverse of those functions, which sounds even more complicated. So it looks kind of a little bit scary, but it's actually a lot easier than the last couple of problems. Because you're really just going to be using a formula here. So you have these inverse hyperbolic functions, and while we're not going to learn that much about them, we will learn how to do a couple of derivatives of them. So what you do is you go to your formula sheet. The formulas from Calculus 1 and Calculus 2. You look under hyperbolic functions, and then you go down here. For all these, we have all the derivatives of the standard hyperbolic functions. Sinch, cosh, tanch, coth, sech, cosec. And then below that, we actually have the derivatives of all the inverse hyperbolic functions. So Cinch inverse, cosh inverse, tanch inverse, coth inverse, sech inverse, and cosec inverse. So the one we want to focus on here is the formula for the derivative of Cinch inverse of u, which is 1 over the square root of 1 plus u squared times du dx. So this is the one we're going to use here. In fact, let me zoom in case it's hard to see on the video. So the one we're using here is going to be this one right here. d dx of sinh inverse of u equals 1 over the square root of 1 plus u squared times du dx. Okay, so we're going to have 1 over the square root of 1 plus u squared times du dx. Okay? And then here, what's our u going to be? Well, u is actually going to be the inner function because we're using the chain rule here. So here our inner function is 5 root 5x. So that's going to be our u. So the derivative of sinh inverse of u using our formula sheet is 1 over the square root of 1 plus u squared times du dx. Okay? Let me zoom out a little bit. Okay, and then because our independent variable here is x, that's going to be our dy dx. Okay, derivative dy dx equals this. Okay, but we said u was 5 root 5x. So plugging in, we have 1 over the square root of 1 plus 5 root 5x squared. 5 root 5x squared. Okay, times du dx. So what is the derivative of 5 root 5x? Well, we might want to do it over here. So our u prime or our du dx, we're going to have to take the derivative of 5 root 5x. So probably the trickiest thing about this is just what to do with the radical. So remember that root 5x, you can rewrite that as root 5 times root x. So we actually have 5 root 5x is the same as 5 root 5 times root x. Now why did I write it that way? Well, to take the derivative, you want to have the constant out front. So what's the derivative of root x? Well, instead of writing it as root x, we can write it as x to the 1/2 power. So we have 5 root 5 times x to the 1/2 power for our u. So then our u prime, or our du dx, is going to be 5 root 5, which is a constant, which just stays out front, times the derivative of x to the 1/2. So using the power rule, we go ahead and we bring the exponent out front, and then we decrease it by 1. Okay, so we get 1/2 x to the negative 1/2. And then if we move that x to the negative 1/2 down to the denominator, it becomes x to the positive 1/2, which is going to be the square root of x. Okay, so that's going to give us our u prime, which is going to be 5 root 5 on the top, and then on the bottom we have 2 times the square root of x. Okay, so there's our u prime, which is the same as du dx. So that's actually this bit right here. I'll write it in blue, times du dx. So plugging in here, we're going to have 5 root 5 over 2 root x for our du dx. All right, and then we can go ahead and simplify our dy dx a little bit here. Okay, so our dy dx, the only thing that we could really simplify here is this radical down there. So unfortunately, they do want you to simplify that a bit. So how do we simplify that? Well, first of all, we want to square it. Okay. So how do you square 5 root 5x? Well, that radical actually goes around the x as well. So what we're going to have is we're going to have 1 over the square root of 1 plus, well, 5 squared is 25. And then for the root 5x, the square root goes away. If you square a square root, it goes away. So we're going to have, under the radical, we're going to have the square root of 1 plus 25 times 5x. And it's not a 5x squared because the x was actually under the radical. So the square got rid of that square root there. But because the radical was around x, it's not going to be an x squared. The square just canceled with the square root. Okay. All right, and then we also still have, over here, we still have a 5 root 5 over 2 root x. 5 root 5 over 2 root x. Okay, now ironically, probably the hardest part about this problem is just going to be simplifying these radicals at the end to get them to look like they do in my math lab. So what do we do to simplify this? Well, first of all, we know that 25 times 5 is 125x. Okay, so what we got here is we got a dy dx equals 1 over the square root of 1 plus 125x. And then we also have, I'm going to go ahead and bring the 5 root 5 over 2 out front. Okay, so I'm going to write out here, I'm going to write a 5 root 5 over 2, because that's just a constant. That is just a constant. And then we still have a root x in the denominator. That is not a constant, so I'm going to write that right there. So now you might not know this, but since these are both square roots in this denominator, we can actually bring this square root of x inside of that square root. And that's the tricky part about this problem, that some people might not know. Okay, so what we've got here is we've got a dy dx equals 5 root 5 over 2. And then we have 1 over the square root of parentheses 1 plus 125x times x. So what did I do there? Well, I actually brought this root x inside of the square root. Okay? And they do want you to do that for your homework. That's why I'm actually bothering to do that. Okay, and now I'm looking at their answer, and their answer doesn't look like ours yet. So I think what they wanted you to do is they actually, I know this is a bit strange, but they actually want you to rationalize the numerator. So what that means is we want to get rid of this root 5 in the numerator. Okay, that's called rationalizing. So they actually want us to rationalize the root 5 in the numerator. So how do you do that? Well, you multiply the top and the bottom by root 5. Okay, so I'm actually going to multiply the top and the bottom by root 5. So I'm going to multiply by root 5 over root 5. So in the numerator, we're going to have root 5 times root 5 is going to give us 5. So in the numerator, we're actually just going to have 5 times 5 now. And then in the denominator, I can bring this square root of 5 inside of the square root, just like I did with the root x. Okay, so on the numerator, we just have 5 times 5. In the denominator, now we have 2 times square root of 1 plus 125x times, well, if I bring this root 5 on the inside here, now I'm actually, instead of just having x, I'm going to have 5x. So it's pretty crazy that they make you do all this, but that's just the standard way to do it. Okay, and then to get our answer to look exactly like my math lab does now, all we have to do is 5 times 5 on the top, which is 25. Okay, so we've got our dy dx equals, on the top we have 25, and then on the bottom we have 2 times, well, they go ahead and switch the order of multiplying inside of the radical. So on the bottom they actually wrote it as the square root of 5x times the quantity 1 plus 125x. Now, if you don't write your answer exactly this way, MyMathLab will usually accept it, but if you get too far from this, MyMathLab might not accept it, so that's why I took the time to show you exactly how they got their answer in MyMathLab, in case if you look at, what the correct answer is, and it doesn't accept your answer, I wanted to show you all the steps so that you will be able to recognize what is different. Okay? So that's going to be our final answer, 25 all over 2 times the square root of 5x times the quantity 1 plus 125x. So, yeah, simplifying the square root was actually the hardest part of that problem. Okay, and I wanted to do one last example. I know this is becoming a long video, but it's good for you to see everything. So let's take a look at example number 6. Okay, example number 6. So for this one, we want to find the derivative of y equals tangent inverse of sine of x all right, and here they're telling us that the absolute value of sine of x is less than 1. Okay, they're just telling us that information. So they're saying absolute value of sine of x is less than 1. And the reason they're saying that just has to do with domain. There's only certain values that you're allowed to plug into these functions. That's not too important, but that's why they're writing that. So what we want to do here is we want to take the derivative of this. So here we've got an outer function, which is tangent inverse, and then we have an inner function, which is sine of x. Now pay attention. Notice this isn't actually sinh of x, the inner function. It's regular sine of x. So that's an important point there. But here our outer function is tangent inverse, so that's hyperbolic tangent. And then our inner function is just regular sine. Okay, notice there's no h. So it's not hyperbolic sine, it's regular sine. So what we want to do here is we want to use the chain rule, doing the outer function, taking the derivative of the outer function, inner left alone, times the derivative of the inner function. Okay, so dy dx is going to be the derivative of tangent inverse, which of course the easiest way to do that is to look at your formula sheet on the first page under hyperbolic functions and look for d dx of tangent inverse of u, which here it says is 1 over 1 minus u squared times du dx. And notice here they say absolute value of u is less than 1. That's why in the problem they said absolute value of sine of x was less than 1. Okay, so 1 over 1 minus u squared times du dx. So here our inner function is going to be u. Okay, so we have 1 over 1 minus u squared times du dx. That's the chain rule. And we just took the derivative of the outer function, inner left alone, times the derivative of the inner function, which is going to be our du dx. Okay, and when you write down a formula like that, you want to check and make sure you did it right. So 1 over 1 minus u squared times du dx, absolute value of u has to be less than 1. So I'm going to write that over here. Absolute value of u has to be less than 1. Okay, and then what do we do next? Well, our u is actually regular sine of x. It's not hyperbolic sine, regular sine of x. So I can go ahead and plug that in here. So we have 1 over 1 minus sine squared of x. Okay, 1 over 1 minus sine squared of x times du dx. Now what's du dx? Well, what is the derivative of sine? Well, it's not hyperbolic sine, it's regular sine. And the derivative of regular sine is positive cosine. So this is going to be times cosine of x. Okay? So here we actually end up with 1 over 1 minus sine squared of x times cosine of x. Now you might think that was the whole problem, and it could have been the whole problem, but you have to use a little bit of a trig identity here to simplify this answer. So even though we calculated the derivative, we need to do a little bit of pre-calculus to simplify this. So I wanted to point out to you, recall that sine squared of x plus cosine squared of x equals 1. Right? That's from pre-calculus. And so this 1 minus sine squared of x, 1 minus sine squared of x is actually the same as cosine squared of x. Because if we take this equation down here and we subtract sine squared of x from both sides, right? We minus sine squared of x here, and we minus sine squared of x over here. Then we're going to end up with cosine squared of x equals 1 minus sine squared of x. That's just a standard thing that you do in pre-calculus whenever you have a 1 minus sine squared of x or a 1 minus cosine squared of x. Okay, so this 1 minus sine squared of x is actually going to be the same as cosine squared of x. I'm going to plug that in up here. And why am I doing that? Well, I can see that I have a cosine of x on the top. So if I have a cosine squared of x on the bottom, one of the cosines is going to cancel out, which will be pretty good. Okay, so we're going to get dy dx equals 1 over cosine squared of x times cosine of x. Okay, but this cosine of x is on the top and the cosine squared of x is on the bottom. So I could rewrite it as cosine of x on the top and cosine squared of x on the bottom. And so one of those cosines is going to cancel out with the square. So we're just going to be left with a 1 on the top and a cosine of x on the bottom. Okay, but remember that 1 over cosine is the same as secant. Okay, so we actually get secant of x. Okay, so we have dy dx equals secant of x. Pretty cool, huh? And so that's actually the whole problem. And the only reason they said absolute value of sine of x is less than 1 at the beginning was just because of that definition of the function. It turns out that the derivative of tangent inverse of u has to have that absolute value of u is less than 1. Otherwise, it doesn't work. So that's why they said that at the beginning. Okay, but here our answer is going to be secant of x. And then the one on your homework is very similar to the one that we just did, but I believe it's going to have Cinch inverse or Cosh inverse, depending on which one you're doing. So for example, if you end up having a Cinch inverse and you're taking the derivative of a Cinch inverse, derivative of Cinch inverse is 1 over the square root of 1 plus u squared times du dx. It's just the same idea as what we just did. It's just got a slightly different formula. The only thing I do want to point out there, though, is when you simplify that, the one on your homework, sometimes you're going to end up needing to write an absolute value. And the reason you're going to have to do that is after you simplify stuff, sometimes you wind up with an absolute value because when you take the square root of a square, you still have to write an absolute value because it's always positive. So maybe I'll do one more example for this video. This video is already very long, but I'm going to do one more example just to make sure you know everything. So example number 7. Example number 7. So for this one, we want to find the derivative of y equals Cinch inverse of cotangent of x. So it's very similar to the problem we just did. It's just somewhat different trig functions. All right, so when you're doing this, Cinch inverse is the outer function and cotangent of x is the inner function. So we're going to take the derivative of the outer function, inner left alone, times the derivative of the inner function. Okay, so what is the derivative of Cinch inverse? Well, the derivative of Cinch inverse is 1 over the square root of 1 plus u squared times du dx. So here our u is actually going to be cotangent of x. So we're going to have dy dx equals 1 over the square root of 1 plus u squared times du dx. So that's going to be 1 over the square root of 1 plus cotangent squared of x, because here our u is cotangent of x, times du dx. So what is the derivative of cotangent? The derivative of cotangent is negative cosecant squared of x. So this is a lot like the problem we just did because it has a regular trig function. Notice this is cotangent, not coth of x on the inside. But the outer function is the inverse function of hyperbolic sine. So that's Cinch inverse. So what we did there is we had 1 over the square root of 1 plus u squared times du dx. Here our u was cotangent. So that's how I got 1 over the square root of 1 plus cotangent squared of x times negative cosecant squared of x. And if you ever forget your Calculus 1 formulas, they're on this sheet, on your formula sheet on the first page. So if you look under derivatives on the first page, right here, and you go down to the derivative of cotangent of u, that's negative cosecant squared of u times du dx. That's the one I just used. Okay, so here that's going to be negative cosecant squared of x. Now, even though this is very similar to the problem we just did, I did want to show you how to simplify this. So how do we simplify this? Well, on the top, we do have a negative cosecant squared of x. And then on the bottom, we have the square root of 1 plus cotangent squared of x. Now you might think that you would leave your answer like this, but that isn't how they left their answer on My Math Lab. So what can you do here to simplify this? Well, first of all, we can just bring the minus out front. So I'll bring the minus out front. And then what we have to do is we have to use a trig identity for the 1 plus cotangent squared of x in the denominator under the radical. Okay, so how do we do that? Well, we go to our formula sheet, and we want to go to actually where it talks about trig formulas. So trig identities are actually on the second page of our formula sheet under trigonometry. So here you have the unit circle, and then below that, you've got some key trig identities. So the one we want right here is the one for 1 plus cotangent squared equals cosecant squared. Okay, so 1 plus cotangent squared of theta equals cosecant squared of theta. So that's what we're going to replace this 1 plus cotangent squared of x with here. That's going to be the same as cosecant squared of x. And why am I writing in terms of cosecant? Well, because I have a cosecant squared of x on the top. So it makes sense to have the same trig function on both the top and the bottom so you can cancel stuff out. Okay, so what we're going to have here is we're going to have negative cosecant squared of x over the square root of cosecant squared of x. Because again, this part that I circled in red here, the 1 plus cotangent squared of x, looking on our formula sheet, 1 plus cotangent squared of theta equals cosecant squared of theta. That's a trigonometric identity from pre-calculus. Okay? And then the tricky part of the problem that's kind of new from the last problem is just how to simplify this. So you would think at the end here, you would think that the square root of cosecant squared of x, you would think that you would just cross out the square root and the square, and you would think that would give you cosecant of x in the denominator and a cosecant squared of x in the numerator. Right? That's what you would think would happen. But when you have the square root of a square, the square makes sure it's always positive. Okay? Which ends up meaning when you take the square root of a square, you have to write an absolute value around it. So instead of writing cosecant of x in the denominator, we actually have to write absolute value of cosecant of x. Which is a little strange, I know. But that's what happens when you do the square root of a square. It gives you absolute value of that. And so in the numerator, here's the even weirder part. In the numerator where we have cosecant squared of x, that's the same as cosecant of x times cosecant of x. Right? That's cosecant squared of x. But because, once again, the square makes it positive, you can actually write it as cosecant, absolute value of cosecant of x times absolute value of cosecant of x. And that's something that you're just allowed to do because cosecant squared of x is always positive. It's always 0 or positive. So you can rewrite it as absolute value of cosecant of x times absolute value of cosecant of x. And there's other ways of explaining this, but this is how I'm explaining it. Okay, and it works on this problem. But there's other ways you can think of it. But anyway, the weird part is the absolute value, so that's why I decided to do one more example on this video. But now we can cross out one of these absolute values of cosecant of x's, and we're going to be left with negative absolute value of cosecant of x as our answer. Negative absolute value of cosecant of x. And that is our dy dx. So I'm going to go ahead and box that. Okay, so I hope this video helped you a lot on this homework. I tried to do an example of each type of problem. Thanks for watching.